So we have when we have studied the dynamic modeling, uh, we have derived finally we have derived an expression in the matrix form. So which denoted the torque. See here, as you can see here, it denotes the torque of joint I and joint J. So in this, so if this can be treated as the generalized expression for the dynamic model, and this is torque for I, and this is torque for joint J. And as you can see, once we write this generalized expression, those terms, or the first term, it is actually denoting the joint inertial tensor. So inertia related to this joints mean this will be the inertia related to joint I. This will be inertia related to joint J. Then this is inertia related to joint I with respect to J, and to J with respect to I. Okay. So the second term, it is denoting the centripetal and centrifugal force. And the third term, we can say it is Coriolis force, and the fourth term is the gravitational force. So that is how when we define, see, we have this is the theta double dot of I and theta double dot of J, and this is theta dot square Lewis. So any theta double dot values are joint inertial part of any term connected to theta double dot are joint inertial tensor terms. Any term related to theta dot square values are centripetal and centrifugal force. And then these terms which are related to theta I, theta j, or theta dot I, theta dot j, it is the Coriolis force, and the no theta value versus the gravitational force. Okay, so that we have to keep in mind once we get into the control of the robot. So the first of all, what we are thinking about is the PID control. PID control, you have studied it in the control system, PID, which stands for proportional integral derivative. So what is actually, we are going to control the uh, arm. Okay, if we consider the case of a manipulator, we are going to control individually. We are going to control the different joints of the arm. So for each joint, there should be an individual PID controller. Okay. So here you can see that you can see the control law, which is actually the expression for this torque, and it is expressed as sum of three terms, which has a proportional constant Kp, then integral constant Ki, and a derivative constant Kd. So that is the PID. Okay. When see, this is a closed feedback system. This system takes a feedback. So the error is measured. Error is actually the desired reference input minus the measured value. Okay. So from the diagram itself, you can see that we have a reference input. We have a reference input R, and the actual output that we get is measured, and it is fed back. So the difference in this thing will be generated as error, and this error every time the system is trying to nullify this error. So the actual condition that is required is E should be equal to 0. So for that we make use of this control law. So this error signal is we are generating a correction signal uh, which is proportional to this error, and also uh, an integral of error, integral signal of error is also taken, and derivative signal of error is taken. So simply giving the proportion, the uh, proportional constant, as the error increases, the signal, the correction will also uh, vary proportionally. So when there is an oscillation, the integration will give us the oscillation, which means the true value, it will not reach the true value. So in order to uh, reduce, see, in the proportional case there will be a shoot up. Then for integral, we have this this particular line as the reference line. Okay, this is the expected thing. So once proportional is there, it may overshoot the, it may go beyond uh, the required line, required value. Then once we try to control it using an integral signal, uh, there may be ripples, and uh, so there will be oscillations. So in order to avoid these oscillations, we make use of this differential uh, constant. Okay, so we are differentiating this error signal. So this error signal is fed to the torque regulator, and therefore in turn, so the corrected signal will control the armature voltage, the DC for the DC motor. See, anyway, you can see that the when we consider the joint of a robot, it is actually controlled by a DC motor. So the DC motor is controlled by is regulated by the armature voltage, and the performance of the torque is regulated by measuring the armature current. Okay, so once the motor starts rotating, its armature current is measured and it is fed back to the torque regulator, so that it can regulate this DC motor. So and you can see some value called phi, which is actually the motor shaft, which indicates the rotation of the motor shaft. And once it is linked to arm, there may be different mechanism like gear mechanism, or for reductions we may use gear or any intermediate mechanism, and this will be the Q will be the actual rotation with the load. Okay, so that is the proportional integral derivative controller for single axis. So this is case of single axis. For if there is multiple axis, we have to make use of these controllers. If we are using the PID controller, we have for each axis we have to allocate an individual single axis PID controller. So if there are 6 axes for the robot, then 6 individual PID controllers should be there. Each one of will be controlling one joint at a time. Okay. Now comes see, we have discussed see how the motor has been controlled. See, motor, it has a field and it has armature. Actually, we are controlling the armature current. We are giving the armature current, and by varying the armature voltage, we are controlling the motor. So see, once the motor is rotated by supplying armature current, you can have this phi value as you have seen in the previous diagram. This is the direct rotation of the motor shaft. Okay, so usually the high speed rotation of motor shaft is not required, has to be controlled a little bit. So in for that case, in order to increase the torque or in order to reduce the speed, we will be using the gear reduction mechanism. So here the motor shaft rotation is reduced by the gear system. Okay. So once the gear system comes into the picture, there will be the viscous friction. Some frictional force will be there and some inertial load will be there. And considering all this, so there will be this opposition for the forces, the rotation, and therefore in turn we will have the load at rotation. So by measuring the armature current, armature voltage is used to change the motor torque. Okay, so you can see that see, this is the internal structure. This part itself is the internal structure of the motor, and you can see that LA IT means IA dot into T. See this expression. See, this is the inductor value, resistance value, and the VEMF, that which is the field winding EMF. So this is actually, this expression gives the value for the armature voltage. So therefore you can see that the armature voltage is controlled by, or it is a function of armature current. Okay. So this is how a motor is being used with the gear reduction mechanism in order to control a robotic arm. Now comes once we try to control this robotic arm, we should have a torque regulator system. See, depending on the load that we give to the robotic arm, the torque should be varied. Okay, see, if a robotic arm, it is a 6 DOF robot, then for 6 joints, different torque should be, for each joint we have to control the torque. So this is a torque regulator system, the detailed view of a torque regulator system. And you can see that we have an input reference value, input reference torque value. So this is the required reference torque. So and we have, in order, when we consider the operation of the robotic arm, it has to move in the clockwise direction or in the anti-clockwise direction. So the direction control of rotation of the motor is controlled using this particular signal. So this is the forward or reverse. So once the reference signal is given, it will be, see, if it is positive, it will go like this. Optocoupler, it is actually it is to isolate. Okay, see, once the motor actually requires high current or high current to run, and the controlling part, usually it may be digital one, and the controlling part does not require that much of current that is required for the motor. So in order to protect the controlling part from this high voltage and high current, we make use of this optocoupler. So here you can see the gating, which is mutually complementary. So by switching this waveform, we can control the direction. We can control the direction of motor. So here you can see that this is the armature voltage, and this is the motor. And once we give the armature current, the motor shaft or the rotation is controlled. Okay. So again, we have to measure, or the current value, the armature current value has to be measured. So what we do is we use a current sensing resistance RS, and we will see, once this current is passed through this RS, we can get the voltage value corresponding through the current sensing resistor. So once that voltage, the modulus of that voltage is taken. So this particular block is actually giving modulus value. Okay, modulus value. So this is taken, the voltage, the modulus of this value is taken, voltage is taken, and when this value is fed to a block where it is divided by the resistance, the current sensing resistor value. Therefore, it will give Vs by Rs, it will give the Is, which is equivalent to the armature current, and there will be one more factor, which is M, which is the gear reduction ratio. Okay, actually we are curious. We can get the correction torque or the error value by considering the robot shaft. Okay, when we consider the robot arm, it is actually controlled by the gear mechanism. So motor will be rotating, the motor rotation speed will be reduced using a gear mechanism, and therefore the friction and viscous force, it will or the friction or the inertial force will be in effect, and therefore the actual loaded torque will be different. Okay, so we measure this loaded torque. Here you can see that, therefore by dividing the Vs by Rs and again by M, which is the gear reduction ratio, we will get the tau L, which is the loaded torque. So that is fed, and we have the reference input and the actual measured value. So it's the difference of these two parameters will give us the error, and we are using a PWM, which means the pulse width modulation. Okay, pulse width modulation to control the motor speed and in turn the torque modulation. Okay, so according to this pulse, when the pulse is on, it will be integrated. The speed is the speed of the motor will increase as it is integrated. The the correction signal is integrated. It will keep on increasing the speed and till the time the pulse width has a positive pulse. And once it is off, this will decrease. Okay. So this oscillator, which is controlled by the PWM, will in turn run the motor, and thereby, according to this PWM, the torque will be controlled. Okay. So that is the torque regulator system. Now we have one more important topic, which is called computer torque control. So we have seen the torque control right here, and this is computer torque control, which actually, so just before explaining this concept, we have to just go back to the previous, one of the previous slide, which is the generalized expression for dynamic model. Here you can see the terms are joint inertial tensor, another term denoting the centrifugal force, then Coriolis force and gravitational force. So when we consider the state model of robotic system, we have four different forces, and in the PID control and all, you have seen that we have a reference input value. We have a reference input value. So this reference input value, in ideal case, it is a static value, which means it will not be changing. It will be a constant value. Okay. So in that case, but here in computer torque control, we have variable reference input. That means RT, which means R will be varying with respect to time. So when the reference input R is varying with respect to time, then that problem we call it as servo control problem. So it is servo control problem. So when we have a dynamic reference point, we call that as servo control problem. So in order to solve this servo control problem, the solution is computer torque control. Okay, computer torque control. So here, in order to apply this solution, the complete dynamic model of manipulator is used. Okay, to cancel the effects of gravity, Coriolis and centrifugal force, frictional force, and inertia. Okay, so all these four forces are nullified, or the effects of these forces are cancelled using the completed dynamic model of manipulator in computer torque control. Okay, so this is very important, computer torque control. We should know this PID, PD, torque control, and computer torque control. So this topic is important. So the computer torque control, actually it relies on the estimated parameters of arm. Estimated parameters means estimated inertia tensor, estimated Coriolis and centrifugal force, estimated gravity force vector, and then estimated frictional force vector. So estimated values, actually this computer torque control is relying on the estimated values of these parameters, these four different forces. And you can see the D, H, C and B. The D, H, C and B, which is actually, it's mentioned here, D is inertia tensor, C is Coriolis centrifugal, H is gravity, and B is friction. So these values are actually the estimated values, or the estimated parameters. That is, D bar is the estimated parameter, H bar is estimated parameter, C bar and B bar are estimated parameters. So these estimated parameters plus the error values. So delta, any delta value mentioned here, delta D is error in the inertial tensor. Okay, so likewise all these parameters has delta value. So the estimated value plus the error value will give the actual values. Okay. Now, in order to cancel the non-linear terms in the dynamic model, so in dynamic model we have non-linear terms. In order to cancel that, we use the control law. So control law, as already we have discussed, it was expression for tau, right? So here the control law is like this: h bar of q plus c bar of qv plus b bar of v plus d bar of q into k into r minus q plus l into r dot minus v plus r double dot. So you have to by heart this control law. And in this you can see certain terms. K is the positive feedback gain matrix. L, it is the velocity feedback gain matrix. And R, it is mentioned here, R, it is the reference input. Okay. Then Q is the actual measured uh, output. Okay, measured output. Then V is actually Q dot. Q, measured output differentiated with respect to time, that is the velocity. Okay, so that is V. And also we know that R minus Q is error. So these are the different terms mentioned here. So the control law is tau is equal to h bar of q plus c bar of qv plus b bar of v plus d bar of q into k into r minus q plus l into r dot minus v plus r double dot. So you can so now you can see the you have seen the control law. Now you can see the computer torque control block diagram. Here also you can see, if you know the equation, you can easily relate it. Or if you by heart, if you understand this diagram, you can easily recreate the equation. So here we have the R, which is, see, computer torque control is basically for R, which is dynamic, right? So it can vary with respect to time. So this R, uh, and we have the correction, right? We have the error sequence. So R, so in the error part, when for the torque regulator part, we take, see here the torque regulator is there. So with the load we are computing the torque, and the robotic arm, it will do the, this is the actual rotation, right? Actual rotation of the arm. So this is taken, and h bar estimated, what is H? Which is the frictional, what were the four forces? B stands for frictional, C stands for Coriolis and the centrifugal, H stands for gravity. Okay, so HQ, then you can see that C Q, here it is Q, and Q dot, okay, CQ, then V is there, V, then BV, right? So once Q is differentiated, taking last class, differentiated, we get V. So BV, CV, this is Q dot, or Q, so this is Q, so CQ. So you just see the previous slide. You can see HQ, CQV, B, H bar Q, C bar QV, B bar V. Okay. Now comes to the D part. So you just see DQ into K into R minus Q plus L into R dot minus V plus R double dot. Okay. So for D, it has to have Q. It has the Q here. Okay. D bar into Q into K into error. right? Error is actually r minus q, right? So r minus q, q is coming here. So this will give the r minus q, right? Then k into r minus q, then L into what else? R minus V is there. So R dot minus V. Okay. L into, see, once it comes here, this is R minus Q, this is R minus Q, right? L into S is there, which is differential function, Laplace, okay. So here, therefore, we will get L into R dot minus V, R dot minus V. Q dot is V, right? Then if you take the integral, you can see that here it is R, okay, R, and S square, it is double integral. So therefore this one will be R double dot. Okay, so if you check the expression, you can see that K into R minus Q plus L into R dot minus V plus R double dot, right? So that is the computer torque control block diagram, right? Okay. That's enough for the case.